Thanks everyone for coming today. This is the seminar series where we're going to cover different research areas going on in the Allen School. And today I have the pleasure of introducing and emceeing for the NLP group. NLP group is quite large and diverse group, but we've pulled together 5 excellent speakers on a whole range of different topics across the field. And so we're going to have these talks now, and there'll be about 8 minutes each with a few minutes for questions. So think of some quick questions as we go along the way. And I think Saewon will kick us off. So take it away.
Thanks for the intro. Hi everyone, I'm Saewon Min. I'm very excited to be speaking here today. And today I'm going to talk about a model that is a foundation for ChatGPT, which we call a language model. It's also often called a large language model or a foundation model, but for this talk I will just call it a language model. So language model is just a next word predictor. So given a prefix of a sequence, we output the next word. So a typical pipeline is we collect massive text data from web sources. So we have billions and trillions of words, and we learn tens of billions of parameters on this data. So given a prefix, we output a probability distribution and maximize the likelihood of the correct word. And once this training is completed, the data is discarded, and these parameters can remember many things from the training data. For instance, it knows that the capital city of Washington is Olympia. So today's language models are great, but they do have many problems because fundamentally, they cannot remember every piece of information from its training data. It can fail to remember many pieces of information. For instance, I ask for a bio of Luke, and then it generates a bio that looks good, but then it has many factual errors. For instance, his PhD university and also graduation year. And this is because the model fails to remember these pieces of information. Not only that, it is often just impossible to be correct because the word changes dynamically, and there is no way the model can learn events that happen after its training. For instance, if I ask, what's the relationship between Google and DeepMind, then ChatGPT says these are separate companies, even though they were merged, because this merge happened after ChatGPT's training was completed. So my PhD work asks, can we rethink data using this language modeling pipeline? And what I mean is, instead of discarding the data, can we keep the data and use it together with model parameters during inference? So instead of trying to remember everything from the training data, we can now locate relevant pieces and reason about them to make a prediction. We call this data a data store to distinguish it from the training data. And remember, this data store is flexible and can change at any time without any retraining. That means now we can scale the model by growing the data store, or we can keep this model up to date by keeping the data store up to date. For instance, by adding breaking news to the data store. We call this model a non-parametric language model because the complexity of the model is flexible and can change with respect to the data store. So these are all great, but how do we design such a non-parametric model? And this is a very challenging problem because the data store is very large. It has billions and trillions of words. And it is impossible to read all the text in the data store. So an intuitive idea is, can we find a more manageable subset of text and read it only? So that's exactly what we do. We use a 2-stage pipeline called retrieval augmentation. Given an input, we use a retrieval system to identify a few relevant passages from the data and then feed them to the model to make a prediction. And now this pipeline consists of many components that are all active areas of research. For instance, how to develop a retrieval system that can better retrieve a good set of passages, how to train a language model to make best use of these passages, how to plug them together, and how to do end-to-end evaluation of this system. These are all important research problems that Europe NLP members, including myself, have been contributing to. So one new question we ask is, can we actually merge these 2 stages into one? And what I mean is, can we have a single model that can retrieve a contextualized word from a data store and directly return it as a prediction? This is very different from existing model that output a categorical distribution over a fixed output for cat. Instead, this new model output a distribution over every contextualized word in a data store. We call it a non-parametric prediction. And this new model creates a range of new opportunities. For instance, now we can predict a phrase instead of a word because this extension is trivial. And also, we can predict extremely rare or even unseen phrases. For instance, imagine this neural model has never seen Harry Potter books during training. Then the model has never seen this phrase because this is a specific spell from a Harry Potter book, and existing models wouldn't be able to predict it. However, this new model can predict this phrase as long as it can understand the surrounding context. I'll not go over too much detail about how to train this model, but please check out the paper if you're curious. So lastly, I want to say a bit about how non-parametric models can enable new opportunities for responsible data use. Currently, language models' training data include lots of data sources that are copyrighted, non-permissive, or even private. Models trained on web data can regenerate copyrighted and private text, and it has been a big problem to the broader society, represented by many ongoing lawsuits. What we propose is to separate permissive and copyrighted data and use a non-parametric language model where model parameters are trained on permissive data only, and the rest of the data is used as a data store queried only during inference. Now, this model has two unique properties. First, we can trace attribution back to the data for every model prediction. And second, we can now remove part of the data from the data store at any time without any retraining. And these properties opens up a new avenue and address many problems related to data use. For instance, now we can credit back to the data creators. Now we can support opt-out request if data owners want. And it can provide strength and fair use defense or any defense against lawsuit. All of this can be achieved while maintaining performance of models that are trained on all web data. Please check out the paper if you want to learn more. Finally, let me wrap up with the future that I am imagining. Scaling is a very important aspect of language models' capability. However, it is extremely expensive, and it's even impossible to do in universities. This is because language models' capability is usually defined by two factors: the number of parameters and the training data size, and scaling each requires expensive GPU computation. With non-parametric models, we have a third factor, which is the size of the data store, and that means now we can scale the model using CPU and storage instead of GPU, which are much more cheaper. Moreover, unlike other two factors that have to be predefined before training, the data store is flexible and can grow at test time. That means now we can scale the model even after training is completed, which was previously impossible. However, scaling up the data store is not an easy problem. The key challenge is in how to scale up the nearest neighbor search to deal with trillions of factors. This is an area where collaboration with systems, algorithms, and databases is critical. So if you work on one of this area, then we should collaborate. Finally, I want to mention my colleagues at Europe NLP who are working on this area, and we are all excited to push it forward. That's it. Thank you for listening.
Okay, we have 2 minutes for questions. Any questions? I can run the mic if you want. Okay, I'll ask a quick question. Do you think the scaling will be more algorithmic advances or more systems advances to pull it off, or do you need both?
That's a hard question. I do believe it's both because what kind of algorithm we need probably depends on what infrastructure we have. Yes.
Any other questions? Thanks a lot, Simon.
Thank you.
So our second speaker is Margaret, and she'll tell us about branch train merge.
All right, so this is fortuitous. I didn't plan it this way, but there's actually quite a lot of, I think, like common motivation between my work and what Sewon just presented. So that's fantastic. But I want to talk to you guys about training LMs efficiently with branch train merge. Similarly, I'll mostly refer to them as LMs, but they're large language models. So before December of last year, I don't think that I would have expected so many people to know what an LM is. But now, usually when people think of an LM, they think of this. If you look a little bit underneath what's going on here in terms of like how they actually get the model, it really reminds me of this particular XKCD comic, which is, like I'm joking and kind of like riffing on it, but it's not necessarily, simple is not necessarily a bad thing, right? Like this approach actually works shockingly well. But there's still some areas, like there are always areas to improve. So what are some things that maybe we can think about improving in the current systems and the current training algorithms? So there are two main things that I'm going to try to focus on here. One is that it's extremely costly, and that can be broken down or looked at in a lot of different ways. One is just sheer dollars. GPT-4, I believe Sam Altman went on the record saying that it costs about $10 million to develop and train. This is, I don't know if he even included, for example, like the salaries of the researchers, but it's a lot of money. Additionally, you need parallel resource use, so you need a lot of GPUs, which are very expensive, and you need them at the same time. And this also brings with it a lot of very difficult engineering. One other thing that I'm going to touch on is the idea of a monolithic LLM. And what I mean is that GPT-4 and most of the LLMs that you'll encounter out there are one single model. So you do this training, and at the end, you get one model out of it, and you can only really interact with it in one way, which is through text. You give it some text in, and it gives you some text out. This is helpful for certain reasons, but it can be problematic. We'll check that into it for a little bit more later. But one other aspect of this is that with this one single model, if you want to edit it, if you want to like remove data from it, if you want to train it on additional data, because maybe like facts have changed or something like that, it's actually very hard to do. And this has a lot to do with just like making sure that the model can remember all the things that you want it to remember, et cetera. So diving in a little bit more, why does it have to be so expensive? Like, who said we needed to spend $10 million on a model? Well, there are now several works working on something that is called scaling laws, which maybe would be better termed scaling trends, which basically just shows that spending that much more money, using that much more data, that many more parameters, which are like elements in matrices that make up the model, all of this really does make the model way better. And one of the reasons why it's last year, sorry, rather 2022, that all this took off so much is just because that's when we started spending that much on these models. One other aspect that's maybe a little bit more technical is that if any of you do more infrastructure type work, when you have so many GPUs running in parallel, you need to do communication between them because they all need to be training the same model. You can't have them all training different things. And that means they need to sync up with each other. This syncing up, this communication is extremely expensive, and it rises non-linearly, like super linearly with the number of GPUs that you're using. Now let's talk about the whole monolithic thing. So this is a very cartoon version of what happens. You're training one model on all of the text. The problem is that if you actually look a little bit closer, text comes in a lot of different forms. Like code looks extremely different from the Constitution, right? Is it really fair? Does it really make sense to be treating all this text in exactly the same way? Additionally, you can think of a lot of scenarios in applications specifically where this is not ideal. For example, if there is any toxic, I'm going to leave toxic undefined here, but use your imagination. Any kind of toxic text anywhere in your training data, your model might generate it. And this can be, of course, very problematic if you're in a scenario with, for example, like a mental health application. And yeah, like it could be just a few data points, and it's very, very hard to put in enough work to like do a really good job of screening out certain kinds of toxicity. And then even if you do that, you have to decide before you ever do any training exactly what you want to filter out, which is really hard. So instead, I'm introducing this idea of an expert language model. And it sounds fancy, really simple idea, which is just instead of training one language model, train multiple and train them on different parts of the data. You can define part or domain is the word that we use in a lot of different ways. I I think that for ease of understanding, we can focus on the idea of a source. So for example, on the screen, you can think of like social media is going to the first expert, health data is going to the second expert, so like maybe health medical papers or something, legal data to the third expert, et cetera. This means, if you use your imagination and imagine that you have models like this, that in theory you could change what kinds of data you're representing even after you've already trained the models. Yeah, so just as an illustration, if your user is in like a health application and they have all this health text that they want the language model to model, you can route it, you can activate only the health expert. If you're saying like, oh, well, I don't want to keep all these language models around. I've heard that these language models are huge. Why do I want 16 of them when I could just have one of them? Actually, you could take the averages of all the individual matrices, and that model actually ends up working really well as well. Sorry, this is the slide. The way that you actually combine these models is that, let's say you have a setting where you actually want to use more than one expert, because this seems quite likely. So this example is of COVID papers. You can calculate sort of how confident each expert is on that text, and then only use the ones that you think are relevant. And then at the end, you effectively can think of it as like averaging the opinions of the experts who are relevant. And as I was sort of alluding to before, you can also remove experts. So let's say, again, you got all this COVID text, maybe you're in a health setting, you've decided that you don't want to use the social media text at all, you can just remove the social media expert. It's not a problem. And same for parameter averaging, just don't use it in your average. Okay, so really quickly, just do a flyby because this is a relatively straightforward algorithm. There is one thing that I've kind of hidden under, which is not super important for you to necessarily really dive into, which is that the best way to do this process is to actually start with a partially trained model. You don't need to do very much, but you need to, for the best effect, to follow that typical training rule of training a single model for just a little bit. And then from there, you make a bunch of copies of that, and you train all those copies on those individual slices of data. And then finally, merge is actually not really anything. You just sort of like put them all together and you're ready to use them. Some quick results that I know numbers are super boring to look at, but it's hard to quantify results otherwise, is that ensembling, which is the method where you sort of average the opinions of the experts that are relevant, performs a lot better than dense, which is the method of training a single model. And what I've actually not even mentioned on this slide is that, lower is better, in case that wasn't clear by the bolding. And I know that perplexity doesn't mean very much to you, so I can't remember actually if I put anything in these slides. But something that I have hidden in this, just take it on faith that this is better, is that the BTM models are also faster. Like, not only do they achieve better, these results were gotten with less resource use. And something that is kind of involved in this is that because I'm training so many different models and each of them individually is training on so much less, I actually don't need as many resources at one time. And that's the source of a lot of this training speed. So that goes back to the costliness. This is unnecessarily complicated because I changed a lot of these figures, but what you want to remember basically out of this is that the algorithm I described doesn't have to be just done once. You don't have to know in advance what all of your data is and then just stop there. You can actually build on your existing models because, like I was saying, taking averages of the actual model, like matrix values works. You can take these averages and then train on new data. And that's like a special thing that you can't really do with a single model, right? So we took all the previous experience that we did, and the takeaway from this is that, once again, lower is better. If you use our method, we're using a lot less hours to achieve the same performance as the single model, just because we've been able to sort of like reuse previously trained experts. And the last question that I'll probably get into here is just this question of like, well, does it actually work to only use like one or two experts, like, are the experts actually learning something that's really specialized, or am I just sort of like making this up? Are they actually all kind of learning the same things? So what this is showing is like a heat map of how active the different experts are for different kinds of data. So the evaluation domains, 0 through 15, are different kinds of data. So for example, COVID papers or something like that. And what you see is that the experts definitely do specialize. You usually only have 1, 2, maybe 3 experts that have any kind of relevance really to this topic.
Thank you very much. Maybe time for one question if anyone has one.
So in the paper, it explains like how like you average together different experts to kind of get your like overall M-force. And I was just wondering, like, do you think that LLMs in general like learn this like maybe like implicitly, like behind the scenes, even without being like trained for it? Like, for example, like in your mind, do you think it's possible that you could take an arbitrary like foundation model and decompose it into a set of experts?
I mean, there's a big gap, I think, between what's like maybe theoretically possible and what I think we can actually figure out how to do. I'm not really convinced that we can actually figure out how to do that. Like maybe it's possible to decompose the matrices in that way. I do think that there's something a little bit like beneficial about doing the BTM step anyways, because like I was sort of showing, when you take the average, you still end up doing better than dense training alone does. So it helps to have that inductive bias that you want to separate those things out. Yeah, I like if someone has like a proposal for how to do that, I think that would be a really interesting analysis.
Thank you. So thank you very much. The third speaker is Oreva, and she will tell us about tokenization and fairness in the era of commercial language models. Thank you.
Thank you. Hi, everyone. I'm Oreva, and today I'll be... Can everybody hear me? Okay, yeah. So today I'll be presenting our work on tokenization in the era of commercial language models. So I want to believe that everybody here is familiar with large language model APIs, at least since like 2022 when ChatGPT was launched. One of the very cool things about commercial large language models and large language models in general is that they're usually trained on tons of data from multiple languages, and even creators of ChatGPT, OpenAI, and a lot of like other companies usually talk about how the model can these models can perform like several tasks in multiple languages. People have talked about like using ChatGPT or other large language models to perform translation. People have talked about like how many languages these models support or can perform tasks with. So another thing about like using commercial large language models is that users can query, you can perform inference, or even like fine-tune on custom data, but this is not free. You usually charge by the number of tokens you can feed in your prompt, or the number of tokens that's like the model generates. So what actually determines like how you're charged, or how like your sequence or your text, your prompt is split into tokens is this crucial step in NLP called tokenization. It involves breaking down a sequence of text into smaller chunks or smaller tokens. Very understandably, there are different like types of tokenization. There's word level for languages that have like white space separators. You can just like separate with white space. The subword, which I'll come to, and then there's character level, where you just break like the text into characters. Yeah, so usually you would, break it down like this text, like collect like all the unique words in your pre-training data and store this in a vocabulary, and then in this vocabulary you map like the words to like unique IDs, and then this is used to like learn representations of like text in your data. So typically what happens during inference is that if you do not with like word level tokenization, for instance, if you do not like have like certain words in the vocabulary, it gets mapped to like a unique token, and then it learns like a unique representation for these kind of words. Tokenization determines the size of like embeddings in the model or in your language model, and typically like a large vocabulary equates a very large embedding. So if you have like if you save lots of words in your vocabulary, then it means that like your embedding might explode, which might not be like very necessary because like some words would only appear like less frequently in your pre-training data. So we only store like very frequent tokens that are in the pre-training data in this vocabulary. So amongst like all the tokenization methods I spoke about, the one that's like very important here today is subword tokenization. It's become the de facto for very recent like large language models, and then it has like some guiding principles. One of which is that like frequent words shouldn't be split into smaller words because we want to learn like good representations for them because like they occur like a lot in the pre-training data, and also rare words. So rare words should not be represented by unique tokens, but they should be decomposed into smaller subwords, and we can learn like compositional representations for them. So in multilingual language models, so the multilingual language models are models that are trained on text from multiple languages. Like multiple natural languages, like English, French, and co. So previous works have shown that like subword tokenization causes disparate fragmentation rates for different languages and writing scripts. By writing scripts, I mean writing systems. So like English, for instance, is Latin scripts. It's written like in the with Latin alphabet. Like Indian languages have like different writing scripts. So we measure fragmentation rate by the number of tokens that results from applying tokenization to a sequence of text. So it means that like commercial languages are usually multilingual, and it means that like languages with excess fragmentation will be represented by more tokens, which would lead to like increased inference and also like increased financial cost of API usage for certain language speakers. Take for instance, we have the same text in English and Telugu on the screen, and then we tokenize this using ChatGPT's tokenizer. We can see that like Telugu has like about like over like almost like 15 times as many tokens as Telugu, even for like the same content in this in both of these languages. So this leads us to like certain research questions. We try to understand like if languages convey the same information with the same number of tokens, and also when there's like non-uniform fragmentation rate across languages, does this lead to like cost disparity for speakers of different languages? And we also try to see how like this fragmentation rate or like these tokenization schemes affect the model's utility. And then lastly, we use some human development proxy to see like the correlation between utility and fragmentation rate and cost. Quickly, I'll run through our experimental setup. So first of all, we compute like fragmentation rate, like I described before, on parallel corpus. That's like I have the same sentences in multiple languages, so the same content in multiple languages. Then we also like do some like task evaluation on like very long form tasks where you have like long sequences. And like I mentioned before, we also like do some correlations between the fragmentation rate and some proxies for like human development in certain countries. So we say that a language is more efficiently tokenized than another language if it uses fewer tokens per sentence in the average. And yeah, so going down to our results. So we kind of like group. So we compute this fragmentation rate over like a lot of languages, and then we group these languages by their writing systems, and then try to like see like what the disparity is. And then we find out that overall Latin script languages, so languages like English, French, or German, are represented with fewer tokens compared to languages in other scripts. So it means that like these languages are usually less fragmented than like non-Latin script languages. And it's very easy to assume that this is like, probably due to like imbalance in pre-training data. So maybe like these models like, have like more data like in English, which is true. But we also do some controlled analysis where we train like our own like custom tokenizers on parallel data from like multiple languages. And then we still see that like it's like very hard to actually achieve like equal or uniform fragmentation rates across languages, even when like you control for like data. Then we also like, try to look at like how these like fragmentation rates affect like cost of utilizing these models. So for the same content, so a lot of language speakers would like be charged like, over 10 times more than English speakers. And then we find out that like these APIs are like cheaper for Indo-European speakers and then speakers of like Latin script languages. So we also do some like task evaluations using like in-context learning. So in context learning, like you feed like a couple of examples in your model to perform a task. And then we find out that in like a lot of languages, we can't like fit in as much text as we need to perform this task because of like the explosion of tokens. And then this results in like lower performance for like a lot of these tasks. So like we see that utility is like much lower for speakers that have like high fragmentation rates. We also, we use HDI, Human Development Index, as a proxy of like, a socioeconomic indicator, and then we find out that the lower the HDI index, the higher the fragmentation rate, and vice versa. So it means that like for speakers in like less developed countries, they would like pay higher to use these models and also like develop like less utility from these models. We also do like some other correlations, and then we generally find like negative correlations between like the cost of utilizing these APIs and then deriving model utilities as like model performance and also the Human Development Index of the country in which language is spoken. So in conclusion, we find that like language model API tokenizers disproportionately favor like Latin scripted languages and over-fragment less represented languages and scripts. And also we think that like the current like pricing policy of like charging each user per token irrespective of like the language that's like irrespective of the language that they speak or they write in is like extremely flawed and unfair towards speakers of over-fragmented languages with these tokenizers. And then we find out that like, these APIs also perform poorly. So it's like you're paying and then you're deriving like almost nothing from using this language, from using these APIs. I think that's all. Thank you.
Thank you. We do have time for one question. Do you have any questions?
Very interesting work. I'm just curious, is it possible that an original sentence is naturally more likely to be written by a native speaker of one language, and that can lead to difference in fragmentation ratio, even if the model doesn't necessarily prefer one language over other? I don't think that's the case with ChatGPT, but just curious.
So like if like a sentence is written by a non-native speaker, will that like result in like over-fragmentation?
Yeah, for instance, if the sentence is about, for instance, an American movie, then it's more likely to be written by an English speaker rather than other language speakers. And if that would make fragment ratio to be better in English.
So I think that like the way like tokenizers are like trained or learned, so they are learned to prefer like tokens that are frequent in the pre-training data. So if an English token is frequent, like if a standard English token is like frequent, was seen frequently in the pre-training data, then it would be in the vocabulary and then it would not be over-fragmented. But if like a variant of English, so people use like speak English or write English in different ways, like we call them dialects. So if a variant of English, if somebody like types in a variant of English, it's very possible that like that text would be fragmented or will be more fragmented.
Thank you.
Okay, let's thank the speaker again. Thank you. Okay, so our fourth talk today will be by Shangbin, and he will tell us about trails of political bias and unfairness in NLP models. So thank you. Take it away.
Okay, thank you for the introduction. Hi, I'm Shangbin. Let's talk about something provocative about language models and politics. So when we think about a typical machine learning pipeline in NLP or language model research, there are typically 3 steps. First, we collect a gigantic size of pre-training data from the web and social media, etc. Then we train a neural architecture on such pre-training data to result in a language model. And finally, we adapt that language model through various means to make them work for downstream tasks. So there is often a lot of artifacts in pre-training data. For example, according to this documentation, the C4 corpus, we can see that New York Times, Los Angeles Times, The Guardian, Huffington Post, etc., they are well covered in language model training data. So this actually brings mixed effects on language models. On one hand, it celebrates democracy as it gives diverse opinions and perspectives for language models to learn from. On the other hand, these political opinions are inherently socially biased and might cause issues for the fairness of NLP applications. So the goal of our work is to understand the political bias propagation pipeline from pre-training data to language models and then to downstream tasks, specifically by asking, first, what role does pre-training data actually play in the political biases of language models? And secondly, does political bias of language models result in fairness issues in downstream tasks? In a nutshell, it's basically that we study political opinions in pre-training data and how they might lead to biased language models, and further to NLP applications that might underserve certain demographics and communities. Okay, a brief introduction of the methodology. So we take the widely known political compass test, which is a questionnaire of 62 political statements. After you indicate your level of agreement to those statements, your response is mapped to 1 point on the 2-dimensional political compass from economically left to right to socially liberal to conservative. We develop a quantitative framework to have language models generate text based on those statements. We make sure that they work for diverse types of language models and also check for robustness, consistency, etc. Okay, finally, some interesting results. So first, our results show that language models do have varying political leanings. In fact, they occupy all 4 quadrants on the political compass. Secondly, we find that language models have far higher levels of variation across social values rather than economic ones. We hypothesize that this is because there is a larger volume of social discussions on social media that is in turn reflected in the pre-training data of language model than economic ones. And finally, the most clickbait-ish thing is that GPT-4 is the most liberal language model of them all. This is also what Washington Post chose to go with when they reported our work. We hypothesized that this might have something to do with the RLHF, alignment, preference, labeling process, as well as annotator biases, which we may or may not have an ongoing work about this. Okay, so now we developed a quantitative framework to evaluate language model political biases. We go on to ask, what role does pre-training data actually play in their biases? So what we do is a controlled experiment. We take the same language model checkpoint and further pre-train it on different partisan corpora from news and social media, and finally evaluate their change in partisan leaning of the corresponding model. So we see that language models do pick up political biases from training corpora. For example, on the left of the figure, we see that Roberta, after being further pre-trained on left-leaning Reddit corpus, it becomes substantially more liberal in terms of social values. Some computational social science researchers suggest that, well, the election of the 45th president of the United States might have led to more polarization in our society. Similarly, we want to ask if language models can also pick up such polarization. What we do is that we divide the social and news media corpora into pre-2017 and post-2017 and train 2 different versions of the same language model represented as an arrow from the pre-2017 one to the post-2017 one. We can see that they do drift further away from the center, which this pattern holds true for more language models across more training data and corpora, meaning that language models could really probably pick up polarization from our society as well. So the first part of our study basically concludes that language models do have varying political leanings, which are picked up from pre-training data to varying extents. Moving on to the second part, we want to ask, does the political bias of language models result in fairness issues in downstream tasks? What we actually do is we take 2 high-stakes, social-oriented tasks, specifically hate speech and misinformation detection. Those data sets come with categories in them. For example, hate speech is divided into which identity or demographic this piece of speech is actually targeting. And misinformation articles are divided into which media source or outlet this piece of news article is actually coming from. What we again do is also a controlled experiment. We take the 4 different partisan versions of Roberta and fine-tune them on this downstream task data set to see if there might be performance discrepancy. Okay, boring numbers. So we first discovered that language models on hate speech detection, they do have varying preferences or performance levels potentially informed by their political biases. For example, left-leaning language models are better at detecting hate speech targeting minority groups in US standards, while right-leaning language models are not doing so well on that front. Similarly, for fake news detection, we see that language models are better at detecting fake news coming from the opposite end of the political spectrum, meaning that left-leaning models are better detecting outright right-leaning conspiracies or whatever. Giving you some concrete examples, when Bernie Sanders is saying something that might not necessarily be factually correct, while the vanilla language model get it right, different partisan versions of language models give completely opposite predictions. On the contrary, when Donald Trump is saying something that's not factually correct, the language models actually switch their predictions, potentially informed by their political biases. So the conclusion of our work is that no language model can be entirely free from political biases. Political opinions and perspectives are always going to be there in language model training data. It is virtually impossible, if not harmful, if we try to sanitize or clean political opinions from language model training data, running the risk of censorship. As a result, there is actually no such thing as debiasing when it comes to language model biases, political biases, and we might just have to live with the fact that language models will always be politically biased. Okay, that's pretty much everything I have for today. Feel free to check out our award-winning paper, shameless plug, for this project. Okay, thank you.
Amazing, amazing. Okay, we have time for questions. That was quite whirlwind and beautiful.
Hey, nice talk. I was
Thank you.
curious about the finding that current LMs have all over the spectrum. So sort of naively, I would expect that most of them are trained from some version of a web crawl with some random quality filters, but not necessarily political filters. So what do you think gives rise to such dispersion?
Okay, exactly. So some more details that I was not able to convey in this talk is that, for example, earlier models like BERT and Roberta, they are more socially, you can say, conservative, like on the top half of the figure, while more recent models like GPT-3, ChatGPT, GPT-4, whatever, they are more socially liberal. So this, in fact, can be attributed to pre-training data because, as you probably know, the training data for BERT-ish models and GPT-ish models, they could be quite different. Because
Sorry, so this is like web data versus
Yeah.
like Wikipedia.
The exact training composition of GPT-ish models, we don't really know, but we hypothesize that it could be attributed to training data distributions. Okay, a lot of questions, as usual, for this talk.
Okay, so if you don't like the question, you don't have to answer it. Does it make sense fundamentally to attribute like a political position to a Markov chain over a bunch of a Markov chain over a bunch of language, where like it's a statistical distribution?
I
Can
see
one
your
say
point.
that a statistical
I see your
distribution
game.
is liberal or conservative, or like it to what extent are we extrapolating? I mean, this is sort of a ridiculous thing because they're being applied in all these contexts. So it seems like somewhere between the fact of what it is versus what it's being applied to, this
I see.
becomes an issue.
I see, yeah. Similar questions was also asked at ACL. I would say here we are not trying to say that a language model is liberal or is conservative as they are just distributed.
Just did though.
No, what I exactly meant is that their generated text in response to those statements show consistent patterns towards one side or the other. I'm not saying that this model is liberal.
When I questioned you on it, you clarified that way, but when you were speaking freely, you said the other thing.
Maybe if you check out the paper, you will see that our language there is more careful and rigorous. But anyways, thank you for the reminder. Language models are never people and will never be. Okay.
I think that's objective. It's all on the path to AGI. So
Okay, cool.
thank you. That's an awesome talk.
Thanks.
So our final speaker, Fatima, will talk to us about a little bit more privacy in language models, and specifically, can they keep a secret? So thank you.
I promise I'm the last speaker. We can all go home after this. So I'm going to talk to you about large language models, surprise, surprise, and privacy. So I'll get right to it. I'm going to start with a real example of a query that was made to
ChatGPT. So this is from VileChat dataset. It's a dataset collected of people's queries and responses to ChatGPT and GPT-4 with their consent. So we can see that someone is asking the model. It's a journalist. They're asking, oh, I'm a journalist for this news outlet. And they're basically giving an entire conversation, a WhatsApp conversation that they had with one of their sources, who's a mother whose child has a certain rare illness. And they're asking ChatGPT to to analyze this and write an article out of it. And just to show you how real this is, I found the actual article that was the outcome of this. So this is a real use case of ChatGPT and GPT-4, and people are publishing articles like this. So in the data set, you can actually find the entire WhatsApp conversation that this person has dumped fully. I've only cut parts of it. It's a very long conversation. And the parts that stand out is the lady, the mother, is explaining that, oh, I have 3 kids. One of them is 8 to 4 years old. The 4-year-old one is the one who has the problem, and they explain the illness in great detail. And they also say that, oh, there is this other parent, Audrey Jones, who might be willing to talk to you about this issue. Also, in the rest of the conversation, this person is very secretive. They're like, oh, don't reveal this about me, don't do this, don't say this. So one problem here is that people clearly don't understand what happens with their data when they share it with OpenAI, and also when they give consent to have it in a data set. But that's a separate issue. What I want to talk about today is the fact that we are giving all this information with different kind of privacy connotations to ChatGPT or GPT-4, and we are asking it to make decisions on what appears in the output. So it's the flow of information from the input to the output that I want to talk about. Now, what was the model's response? So the model generates a long article. This is part of it. It reveals the 3 children details, the ages. So I believe even with this paragraph, you might be able to re-identify this person, but that's a separate discussion. And it also reveals the name of the second person who did not even consent to, this person didn't even talk to them. So the model response reveals this. Now, to compare the model response with the article that this person released, I found many paragraphs that were used verbatim without any kind of editing from ChatGPT's response in the actual article, but the part about the name was removed. So the human intervention kind of removed the person's name, but this, one example of exact copying you can see here. So the problem that I, again, want to emphasize is that we're more and more trusting these models. We're giving them information, and we're expecting them to reason about this and tell us, what can go through and what should not go through. And if we get sloppy about it, and if we trust the models too much, we might release information that was, not appropriate to be released. So the question is, the question for the models are, should I share this or not? Is it sensitive? Is it necessary for me to share it or not? So what we expect the models to do is to reason about what information to share, for what reason, and with whom, in what context. So what is important here is the context. And in order to actually quantify this and kind of build a principled framework of evaluating language models, we look at the privacy policy literature. So in 2004, Helen Nissenbaum proposed this theory of contextual integrity, which quantifies privacy in a context. So what she says basically is that privacy is the appropriate flow of information. And she contends that, deciding if a certain piece of information is sensitive or not in and of its own in a static way is problematic. For example, your heart rate. You would reveal it to your physician, but you would not go revealing it online. And this is what we build our data set and a benchmark for large language models on contextual integrity and if they can understand privacy in context. So what this means is that we build a data set that has multiple tiers to test for different things. We start very simple with questions like, if someone's SSN is released, does it meet privacy expectations? And then we ask GPT-4, how much does it reveal it? It says, okay, it should not be revealed. Then the next tier is that we add an actor and a purpose. So we add more context here. So we ask, is it okay if we share, someone's SSN with their accountant for tax purposes? Then the model says, yes, now it's okay. Now the third tier, which adds more nuance and is more convoluted, builds on the fact that context, when we're reasoning about privacy and when we're reasoning about information sharing in general, is not just who I'm sharing it with. It's also the belief graph that we're keeping in our heads. We're tracking, does this person know this thing? Does this person know this thing? So there is a layer of theory of mind involved here to track who has access to what information and then to reason on that. So the third tier involves like more convoluted theory of mind scenarios, and like Bob confides in Alice about this thing. Now, is it okay for like Alice to reveal a secret to Jane to make Jane feel better? So scenarios like this. And then the final tier, it's more practical, and we also kind of make it more compound by adding different information types. So some parts of the information are needed, some are not. So we want to measure a privacy utility kind of trade-off, if the model can understand what needs to go through in the output and what doesn't. So we build these meeting scenarios. It's like a meeting assistant that is trying to take meeting notes and then send everyone's to-do items to them. So it has to make decisions on who should do what and who should have access to what information. And then we ask the model to separate out people's to-do lists and what they should remember. And then we end up getting things like, oh, Alice, remember to attend your own surprise birthday party. So I'm not going to really go into the details of the results. You can look at the paper, but I'll just want to show you some interesting findings from the theory of mind scenario. So in these scenarios, we have two people talking about a third-person secret. And the model has to decide if it's appropriate to reveal another person's secret in this setup. And we built factorial vignettes, which what they basically are is we iterate over different secret types, like if it's a disease, and like different actors, if it's coworkers talking to each other, family members, and also different incentives of revealing a secret, like to reveal it for money or to reveal it to help someone. So the takeaway from this very complex heat map is that we find that the model tends to reveal information most of the times if the information is going to help someone feel better. So the models are so aligned to be helpful that if you really make it believe by revealing a secret, it's going to help this person in some way and make their lives easier, it's going to reveal the secret. We also find that secret revealing is highest for secrets about sexual orientation, which we kind of assume it's because of trying to raise awareness. But it tends to not reveal secrets at all. Like you can see the all 0. When you have scenarios where you have coworkers talking to each other, which kind of makes sense, you won't reveal secrets to your coworkers. And also when the secret is about self-harm, which we kind of assume is also because of the alignment and the way that the models are guardrailed. Now, one thing we find is that it's not the lack of knowledge that causes this behavior, it's the fact that the model cannot operationalize it. So we ask it what it knows, who has access to what information, what is private, what is not. It can answer all of those separate questions correctly, but when it has to put them together in a cohesive narrative, that's where it fails. Also, again, we believe that the model trying to be so helpful is what is important here, because looking at social sciences studies, people, like in real life, real people, reveal secrets as a form of moral punishment or judgment, but models do it to be helpful. They don't do it in a way for revenge. And also, the normal Band-Aid that is used for LLMs, take a deep breath, think step by step, all of that chain of thought reasoning is not effective here at all. In fact, it makes it worse. We see worse secret revealing behavior when we tell the model to think step by step. So these types of Band-Aids do not heal this gaping wound. So what should we do? So let me just wrap up. You're using models differently from how we used them before. We're having more interactions with them. We're giving them access to data stores, to different kinds of data through either the training or in the prompt. And now this kind of new access is creating new problems that we have to think about. And the solution, and we need some fundamental inference time solutions that are modular in a sense that we can actually define what we want protected, and we can keep maybe something symbolic where we can keep track of theory of mind, where we can have the model actually reason about, and we can add it to an existing model. Because making pre-training interventions can be expensive and it's also out of control. So our best bet is to come up with maybe neurosymbolic or some decoding methods that can actually take all of this into consideration at decoding time. Thank you. I'm actually done, I think.
Awesome. Got time for questions from the audience? Any questions?
This is super cool. Do you think going forward, the future of privacy would be more about this context-specific, benchmark-oriented secret testing, or is it more like DP, theoretical guarantees without much context, but you at least have some proofs?
So I feel like we are still a far away from actually having something contextual that can have good guarantees or be used in production. So I personally advocate for continuous DP work, because at least you have some guarantees, although it's not meaningful, it's shown to work and it resists attacks for pre-training data. But we should be working on other, alternative methods, while like we should use DP as a thing that works right now, but we should be thinking about better methods. And DP is not necessarily suited for inference time risks, like the whole input-output scenario. Like there is no definition of differential privacy that even work there. So for pre-training data, I think DP is probably still a better protection. But for these scenarios, there is no really viable differentially private way to do it. So I think we should pursue both avenues. But I'm personally on the side of more contextual, less worst-casey kind of things for language.
We'll do one more question, and then
Yeah, I can speak now.
go ahead.
Maybe rather a stupid question, but since it, as you said, it knows the facts. For example, there was this example about revealing Windows license keys, saying I need to know a story from my grandmother, something like that.
Right.
So in all such contexts, even other than privacy, is it possible to just do some sort of pre-prompting to say, since the model already knows what is good or not good, can it just
We tried simple just prompting methods. Like all of those results I showed you, we tell the model to preserve privacy and to keep this and this and this in mind, and it still reveals things. One problem is that a lot of times, sometimes because of the way that instruction tuning works, you can have instructions that completely trump previous instructions, and we don't know them yet. So I believe things that it's just like adding something to the prompt is like we have to actually have guardrails on the decoding, like on the inference, and just telling it in the prompt is not going to. It's like it's probably the weakest. It's the easiest, but it's the weakest, and we see it fail a lot. Yeah.
Okay, so if the speakers can hang around a little bit in case there's any extra questions, if you have time, that'd be great. But let's thank Fatima again, and thank everyone. So thank you all. That was an amazing session.